The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. This video is about the process of isostatic rebound, which ultimately leads to the uplift of a mountain range and allows us to find fossils of marine creatures on high mountains. And as with all other videos, I would like to point out the opportunity to write to me if you have any questions or comments. My email address is written down on the first page of the video or on the website. Many of us have probably been hiking or mountaineering in the Alps or other high mountain ranges. Here, for example, is a picture from the Dolomites in Italy, where I was hiking in the Sella Pass area a few years ago. The Sella Group is a plateau-like mountain range that averages over 2,500 meters in altitude. But these rocks weren't always at these heights. Originally, the rocks were deposited in shallow sea basin, and in this video I want to show how they came to be so elevated today and why, with a bit of luck, we can find shells or other remains of marine life such as ammonites or corals up here. What's striking about this picture are the more or less horizontal layers throughout. They are occasionally slightly tilted, meaning inclined, and sometimes there are also thrust folds. But folds, really large folds, are hardly found here. Overthrust, such as this one here, which can be seen on a wall on the Sella Plateau, at least show that the mountain range was also narrowed. In other places in the Alps, such as here above Innsbruck in the so-called Northern Calcareous Alps, the layers are often significantly more inclined. This is because the Northern Calcareous Alps, as part of the huge Eastern Alpine nappes, were much more under compression than the Dolomites, while being transported far north. This certainly also led to the formation of large fold structures. I'll come back later to this. The phenomenon of uplift can also be clearly observed in many other places. Here is an example of an uplifted plateau, this time not in the Alps, but in Oman on the Arabian Peninsula. The rocks here are of course quite comparable to the Dolomites or the Northern Calcareous Alps, as they formed at the same time and in the same ocean, namely the Neotethys, just like the examples from the Alps just shown. The only difference is that this part of the ocean was much further south. On this plateau in Oman, I was able to see some beautiful fossils, exactly the same type of which could be found in the Alps. But anyway, I haven't found them there myself yet, so I'm showing the ones from Oman. These are large shells called megalodons, and they are also called cowprint shells because in cross section, as here to show, they look like a cow's footprint. These shells show us that the calcareous sediments were deposited in a shallow ocean basin, which today lies at altitudes of more than 1,000 or 2,000 meters. How do they get there? That is the question of this video. How do the mussels get to the mountains? This of course has something to do with the development of mountains, and to explain that, I'd like to take a closer look at the Alps as a whole. Here we see a digital terrain model of the Alps, a topographic map created using satellite data on which the mountains and valleys are particularly clearly visible. Some striking lines immediately catch the eye. Like here, for example, one of the main valleys in the Alps. This line has a tectonic origin, and it is here that we find the seam between the two continental plates that collided. This is called a suture, which comes from the Latin word sutura, means seam. Accordingly, this line is also known as the periadriatic suture or periadriatic lineament. I'll overlay the division into plate tectonic units on the map. There we can see that the peri-Adriatic lineament borders the parts belonging to the Apulian-Adriatic plate. To the north are the units belonging to the Penninic Ocean, which is the greenish colored area. And then further north, everything belonging to the European plate. I'll go into more detail in a later video about the Eastern Alpine nappe, which belongs to the Apulian-Adriatic plate and was thrust onto the Penninic Ocean as a tectonic nappe. So here two formerly separate continents, Europe and the Apulian-Adriatic plate, lie directly next to each other, and in between are the remnants of an ocean that once existed between these two continents. And this raises the question of how this mountain range came into existence. How did it form? I've provided a schematic illustration of the development of a mountain range in this short video. It begins with plate drift. At some point, the continent reaches the subduction zone, like in this moment, and collides with the other continent. This then leads to the overthrusting of the two continents and the formation of nappes in the continental crust. With the slab break-off of the oceanic lithosphere, the collision ends and the uplift of the mountain range begins as a result of isostatic adjustment. Here are the most important stages again. The continents move toward each other, resulting in a collision, whereby one continental plate is subducted beneath the other. Initially, the entire stack, including both continents, is pulled downward because the oceanic lithosphere is still attached underneath. During this time, the convergent movement of the two plates continues, and in both plates, nappe structures are formed. That means tectonic overthrusting and stacking of rock units occur. At some point, however, the force is no longer sufficient for such overthrusting, and the convergent movement stops. This is a moment when the oceanic lithosphere breaks away and the slab break-off leads to its descent into the mantle. The oceanic lithosphere behaves very different from the continental plate because it is heavier than the asthenosphere beneath it and can therefore literally fall downward. This process is called slab break-off. I'll discuss this phenomenon further in the context of subduction. Only after the slab break-off has occurred, as can be seen in the last two steps, does the actual uplift of the mountains begin. And this is a consequence of the isostatic compensation. In the previous chapter on isostatic compensation, I already showed this illustration, which clearly explains why mountain ranges are lifted after collision and slab break-off. Above the theoretical compensation level, each of the columns, shown here, must have the same weight. As long as the oceanic lithosphere is still attached to the continental lithosphere, it is pulled downward, creating an imbalance. The moment the oceanic lithosphere breaks off, the continental crust literally springs upward because it has a lower density. It's like pushing a styrofoam plate down in a swimming pool, and it springs back up when you release it. Isostatic compensation occurs because some mantle material has to be pushed in from below to compensate for the weight above the adjustment surface. And this then leads to the uplift of the mountain range. This is exactly what happened with the Alps and all the other high mountain ranges on Earth. To understand these movements, it may be useful to review chapters 2.1 on isostasy and 2.2 on isostatic compensation of this video series. In the next video, I'll start with a discussion of plate boundaries, starting with divergent plate boundaries where it all begins, a rift valley. Before that, however, there is an overview of the different types of plate boundaries. This time, thank you for listening, and I'll be happy if you stick around. I recommend continue with the video on the overview of the plate boundaries.